welcome you all. Thank you for making it out to the talk. Open source software and national security. These are two topics you generally don't hear in the same sentence. But as we heard in the keynote this morning, there's actually quite a lot of work being done in this area, in the federal government, in the open source communities, around government, and in and between agencies, both inner sourcing, open sourcing, some closed sourcing. And there's some real nuances and difficulties in some parts of the federal government. It's an evolving process. As Alvan said this morning, we're going to be working on this for a while, and I think the best is yet to come. My name's Ian Lee. I'm a computer engineer at Lawrence Livermore National Lab. For those of you that maybe aren't as familiar with what that is, we're actually only located about 50 miles east of here, out in Livermore, California. And we're one of the Department of Energy's research labs. We grew out of the aftermath of the Manhattan Project. Los Alamos National Laboratory was the first laboratory founded back in the 1940s and 50s. And our mission is to develop and solve the big science, the big computing problems of our time. So we're located on 1 square mile out in the eastern part of Livermore. For those of you that have been out there, it actually just got incorporated and became officially part of Livermore in the last few years. It was a former Air Force base that they converted over and that we currently use as our home. We have about 6,300 employees, and we're one of actually 17 DOE national laboratories across the country. In the orange, or in the bottom left, you can see we're actually one of 3 national laboratories, along with Sandia and Los Alamos, which are responsible each year as one of our main objectives, reporting to the president on the state and readiness of the nuclear stockpile stewardship. So the idea here is we have these nuclear stockpiles, these weapons. Since the early 90s, you can't go out to the desert and test them there. So what have we done to grow out of that? Well, we've had to develop big computing simulations to solve these problems and to be able to answer the question, if called upon, would this stockpile be ready? You may also have seen us recently in Star Trek Into Darkness. We've done a little bit of work there. So we actually, this is a shot from inside of NIF, the National Ignition Facility, where, for those of you that saw the movie, the warp core is sort of the focal point there. So as this is a national lab, we do a mixture of, obviously, closed source. People know that we also do open source and what happens in and around those communities. The realities are that we can't solve the problems all on our own. We have our own set of problems to actually solve the applications, the big physics questions, the big science questions of the day. And actually, having to reinvent everything that the open source community has built already would be a ridiculous waste of taxpayer dollars. And as was mentioned in the keynote, trying to reduce the duplication across the federal agencies is one of the main goals as we strive forward into the future here. So because we're a national laboratory, because we grew out of a time in the nation's history where we had nuclear development happening, we actually have quite a lot of silos. We have many pillars inside of just Lawrence Livermore, between Lawrence Livermore, Los Alamos, Sandia, the other national labs, and other parts of the federal agencies, right? So we have DOE as a whole, we have the intelligence community agencies, we have DOE, many parts of the federal government. We all sit in these individual silos. And what open source has allowed us to do is actually to bridge those gaps, to start piercing holes into these silos and to make the code, the resources, and the knowledge that we're having to develop to solve our problems available more broadly. So what does that look like? Well, obviously we're here at GitHub Universe. The open source community as a whole has really embraced Git and GitHubcom as a hosting platform for developing software. Internally, though, the picture is often very different. As I mentioned, we were founded back in 1952 in the aftermath of World War II. And at that time, the largest supercomputers, what was actually qualified as the first supercomputer, the CDC 3300, was 1 million instructions per second. Right? That's, I don't know, your cell phone back 10 years ago sort of time frame, and that's what was a supercomputer at the time. Nowadays, obviously, we have much bigger systems than that. Currently, our largest system is 16 petaflops. And actually developing on those systems is not something that the general open source community, general developers, folks that are developing software for your laptop actually have to deal with. So I mentioned, we've been around for 60 years, just over 60 years. And it's been an evolution of computing equipment, technology, and we've tried to be, this entire time, at the forefront of that development. We have had some of the earliest computers delivered and on our site, and we've done some of the most interesting problems. So moving into simulating mixing of fluids, of dynamics simulations, math simulations, meshing, and all of this really grows out of the need to have these large computing resources available, right? They're not necessarily designed originally for solving these sorts of problems. In fact, a lot of the supercomputers in the last 20 years have been collections, large of hardware. You essentially just take many CPUs, common CPUs like you would find in your desktop, you put them all together, and you put them all facing at the same problem all at once. The petascale system that we have right now, our largest is Sequoia. It has 1.6 million CPUs in it. And it's actually on the top 500 list for 2012 for a limited time. We've had some of the biggest systems, but what does that actually mean? So to give you an idea, for those of you that are familiar, in the HPC world, one of the biggest lists, sort of the Grammys, if you will, of the supercomputing world of HPC is the top 500 list. This is a list published twice a year, June and November, that highlights and ranks the largest supercomputers, the largest high-performance computing systems in the world. And in the last 20 years, we've had, at Lawrence Livermore, three different systems on the top 500 list. ASCII White from 2000 to 2001, Blue Gene L, an IBM system from 2004 to 2007, and again, Sequoia, our largest 1.6 million core system, 16 petaflops, about 100 petabytes worth of disk storage on various different file systems, about 10 different file systems we have internally. And these are the systems that we run on. These are the systems that our scientists, our engineers, our researchers that are doing research, including but not limited to, you may have heard in the news recently, the Cancer Moonshot Initiative is a collaboration involving Lawrence Livermore and involving these large computing resources. So having a bunch of hardware, as I said, you can take a bunch of CPUs, you can put them all together in a rack. Turns out in the case of Sequoia, it sits on about 4,500 square feet. So to give you an idea, that's about the size of a house plot in California. So it's a good chunk of real estate. But in order to actually do anything with it, to do anything useful with it, you actually need an operating system, right? So Linux, Mac, Windows are operating systems. We have actually had to develop our own. The earlier version of this was called Chaos, the Clustered High Availability Operating System. It was grown out of the Linux project at Lawrence Livermore. It's a collaboration between the national laboratories. Again, when we're not the #1 spot, we're also often rotating amongst Sandia, Los Alamos, Oak Ridge, with the Titan supercomputer most recently at Oak Ridge. And the reality is there's kind of a different software stack than you're used to developing with on your Mac and where you're the only user. And the reality is that we have a need for actually scheduling out these jobs, for doing things like high availability file systems, for low latency interconnects. One of the biggest challenges in computing today is I/O bandwidth. We have both incredibly large data, again, file systems on the order of 10 petabyte single file systems that we have to deal with. We have network connections between these 1.6 million CPU cores, and how to actually work with that and not have the contention that would slow down an application. In something like a Hadoop environment where you're maybe not necessarily caring about the most optimized latencies between things, you can sort of distribute out the work and collect it back. It's a very different computing environment to a large MPI environment like this, where you're passing messages between these cores and broadcasting across the entire system, doing reductions. and doing these large operations. So we've actually built our own stack that we develop in collaboration with, again, Los Alamos and Sandia to have a unified operating system stack. And the reality is we build right on top of Red Hat Enterprise Linux in our case. We take the base set of packages there, about 3,300 packages, remove some that we don't need, but we also add a lot on top of that. There's quite a bit of repackaging of systems to make problems, again, that don't manifest on one server running, let's say, even 32 cores in the same box, that do appear when you start scaling that out to 4,500 square feet of computers. And so we've had to conquer those problems. And the reality is that a lot of this is in collaboration with vendors, providers of these systems. So I wanted to highlight a few of the open source projects. Again, we have had to build these computer systems to do our own physics simulations. And a lot of the pieces that have fallen out of this have made their way into the open source community and actually have done that for quite a while. So Slurm is a job scheduler. This is a resource manager to actually, in general, you're not running, one user doesn't have the entire system all at one time. The reality is that most of the time, it's subdivided up. You might have, let's say, 100 users running simultaneously jobs that maybe I need a few hundred nodes, someone else needs a couple of thousand, but you've got 1.6 million here. So actually dividing that up to be able to schedule all that work to happen efficiently and to schedule things, to schedule different resources that are needed is a common problem. And it becomes quite interesting when you have these sorts of large. So Slurm was originally started back in 2001. Obviously, at that time, there was no GitHub because at that time there was no Git. And so it started as an internal project. You can see in the graph here, this is just a commit that you can get off GitHubcom site. And starts back here in 2001. And you can see kind of somewhere around 2011, actually, this was of one of our very successful technology transfers where a product, an open source product that we had developed internally, a few of the developers went to found a company where they've actually been able to support this across the entire world. So there's HPC centers in Switzerland, in France, in the rest of Europe, in Asia, that are using Slurm to do their job scheduling and their resource management across their systems. Flux is a currently prototype system. It's in very active development. It's actually a framework of components, and it's designed to be the evolution or maybe the potential successor for Slurm at some point. And the idea here is when Slurm was developed back in 2001, some of the things that are commonplace now were not common in computers, even in supercomputers at the time. Things like GPUs, things like strange new memory file systems. All these sorts of things weren't necessarily something that the resource manager knew how to handle. And for the most part, they've been added. There's support for them now for scheduling, OK, I'm going to need a job. I need this many CPUs. I need this much memory. Now you can handle, OK, I need these GPUs. But as the types of devices that we're seeing come out of the open source community and the software community as a whole continues to evolve, there's increasing, set of requirements and set of pieces. So Flux is the evolution, again, of Slurm, of job scheduling, where the idea is that you can subdivide out pieces that you can make plugins, as is very common in the software development world nowadays, but again, was not in decades past, to have these modular applications and actually put together the pieces. If a data center has some new thing, as we move into quantum computing and these sorts of things as we go into the future, how do those sorts of resources play and how do you actually schedule? CFS on Linux. So one of the things that we deal a lot with is these large file systems. And we have everything from millions and millions or billions of tiny, tiny files, right? Essentially, let's say little identifiers, little messages, little pieces of information from these large multi-physics simulations. We also have environments where or simulations where we have very few but very, very large files. And the reality is that the file systems that are available in the commodity world, in the open source world, in your Mac distribution, Red Hat, don't always necessarily solve the same problems. So for example, if you're a Linux user, you might be familiar with the ext4 file system, and you think, well, why don't we just use that? That's good enough. It turns out it may be a fine file system. It's certainly very battle hardened. However, it only supports up to volume 16 terabytes. So we're talking about petabyte file systems, order of a magnitude greater. You can't use necessarily these same products. And so what we had here again is the ZFS on Linux project grew out of the ZFS on Solaris, or the open ZFS community. It was originally available through Solaris back. The development actually started in 2001, was released to Solaris in 2005. And the reality is that Lawrence Livermore actually led the work to port initially ZFS to Linux. So that work began in 2008. And in 2011 is when the first actual release happened. You can see there's a nice spike right there around the time it got released. And we've seen a fairly steady community of adoption. And one of the great successes here is that as of this year, it actually ships now in Ubuntu. So it's now become as easy to get and use this file as apt-get install ZFS and enable the pooling. So, but again, this is a project that grew out of Lawrence Livermore, is managed by Lawrence Livermore, at least the Linux portion of it, in collaboration with many open source, many vendors across the world. Another tool that we have is called Spac. This is our supercomputing package manager. And if you're a Mac user or a Linux user, you might be familiar with Yum. These sorts of package managers are great when you have a single system, typically aimed at one particular service, right? You have a web server or a database server, and that's kind of the only role. You probably have fairly limited, fairly restrictive access rules in terms of who can actually get into the box, who can log into the box. And the reality is that in these big HPC environments, you have potentially hundreds or thousands of users simultaneously using the same systems, and in reality wanting their own applications to be able to be built and run. So whereas we have in Mac brew to brew install some package and it will download tarballs and build up and compile locally, Spac does something fairly similar where it actually will download the packages and can build you a tree. But the reality is if I'm user A and there's a second user B and we both want to build up two tools, in the general commodity world, that might be fine, right? I have two different things and I'm mostly just going to use the default configuration. I'm probably not going to tweak things. In the HPC environment, there's oftentimes multiple MPI versions, multiple platforms that we care about, IBM versus Intel, Linux versus Blue Gene. We have several different versions of each package. We have up to 7 different compilers, Intel, GCC, Clang, various other open source projects that are being done for compiler work or MPI work. And when you have things like applications that have 48 dependencies, you end up with combinations of like 7,500 possible ways to combine and compile and link all this together. And the reality is that if you had to do it where every user did this individually and make that available, it doesn't scale very well. So Spac was developed to solve that problem by building some of the dependency requirements into the actual system. Once we've run these big simulations, what do you actually do with that data? And how do you share that data across different researchers, different collaborators, universities, other government partners, and for that matter, the rest of the world? So ESGF is a Lawrence Livermore originally instigated. It's actually a collaboration between several agencies, Lawrence Livermore, NASA, several others, where we're trying to distribute out these large petabytes worth of data in a distributed way across the world where federated sites can work together. It's sort of distributed AWS style where you have a bunch of data and you can get it out from various different points. And the idea here is to enable international collaboration, to have this sort of decentralized database around, in this case, climate science data. But we have several other projects that are working with other types of data, geodata. Again, as I mentioned earlier, we have some work happening in the cancer and the bio realm, and how to share that data safely and securely across the different environments is some active research that we're pursuing. Again, as we build up these large simulations, we have this large amount of data coming out of our systems. How do you actually visualize that? How do you visualize a petabyte of data? I mean, even just wrapping your head around that number as a whole, it can be difficult. Even a terabyte, or a gigabyte for that matter, actually grok that many zeros is quite a challenge. I mean, to actually wrap your head around what that really means. And so what we've had to do is actually develop tools. In this case, Visit is a visualization tool that we developed to actually visualize and do computations and do reductions and different sorts of overlays and graphics around these large multiphysics and other associated codes. So that work is done in a very large community. I wasn't able to include the GitHub stats here. We're actually in the process of moving it from SVN. Again, these are a lot of the projects that we have grew up in a time when Git and GitHub did not exist. We have projects internally that have been around for 10, 20, 30 years that this software code base has actually been alive. And there is some amount of effort to move that forward, to move a big code base. And some of the things that you could get away with doing at the time with SVN maybe was considered bad form, but you could do it. Things like checking in binary files into your source code. At the time, it worked. Nowadays, generally considered bad form. There's other better ways to do it. To give you an idea, this particular one, the source code, the SVN repo, if you try and check out the whole thing, is about 70 gigabytes. So that'll take you a little while. To give you an idea, GitHub's limit is 2 gigabytes for your Git repos, in case you didn't know that. So again, underpinning this research, this HPC development, simulations that we're doing, the data science that we're doing, are a number of research activities. There's a lot of work being done in mesh refinement, in adaptive meshing, in visualization of flows of different sorts of materials, how things react to different sorts of physics cases, how heart valves operate. So there's some work that we're doing, a project called Cardioid, that is actually simulating the human heart and how it beats over time, and having a mesh that represents that heart and how that changes over time and how you evolve that simulation over time is some active work that we're doing in collaboration with IBM. And a lot of that work is happening out in the open. A lot of these projects have been moving into the open or have existed in the open for a long time. Talking about the 2% of our projects moving forward being open sourced as a federal requirement is a very interesting opportunity. And I think code.gov will give a lot of visibility into some of these projects in a way that will allow us to see what else is happening in the federal government, both for ourselves to see what other sister agencies are doing, but also for the public, the people, to see what is actually being in open source communities that have grown up around federal research and national laboratory research. So to give you an idea of what that looks like, our GitHubcom/LLNL is our organization. And we actually have, again, a long history of repositories. At the moment, we have just over 90 repositories there where we have source code. In the last year, we've actually added 40 of the repositories there. Before that, our first one that showed up on GitHub was created in 2008. It's recently been moved into this organization. And you'll see a wide variety of code. There's quite a few different projects. It's a lot of C and C++. These are the things that you're typically using on HPC that you're doing these simulations for. You want that performance. You want every iota of performance. A lot of cropping up like Python and Shell to actually do the sorts of integration and glue projects that tie all these things together. Spac is a Python project. We have some shell code for actually doing build and test and integration. We're very heavily involved in the BuildBot community to actually build and test these different systems and configurations and combinations on many different compilers and platforms. So we're working very closely with the open source community. And we're very excited about the opportunities that things like the federal source code policy will make available. Interesting is with the consolidation work, we've been working about the last year to consolidate and bring a kind of a central presence. This was just before the federal source code policy was put out on GitHub for comments. And that was in March. We started some of this work in December. And we've actually started moving and migrating some of our repositories that have sat in SVN or sat as tarballs sitting on a website, which is obviously the way developers want to work with them in 2016. And we've been migrating them and moving them into these sorts of environments that, in general, the open source community has adopted long ago, right? We have, 150 integrations that are available through GitHub. To actually take advantage of that is a lot of work that we now don't have to do internally to support the tooling and infrastructure to do these sorts of tasks, to do continuous integration, to do documentation, things like readthedocs.org, to do website hosting. So even the GitHub Pages project is something that we're able to use along with Jekyll and Markdown to actually build our websites and build some of our documentation, both internally as well as externally. So again, I mentioned some of this work started just before the source code policy. And one of the early things that we wanted to do, again, we have a long history here, and it's going to take us some time to get everything sort of pointed in the same direction, visualized and displayed in the same way. But what we've actually seen is we have currently about 8 major organizations on GitHub that are associated with Lawrence Livermore. Think places like ESGF that I mentioned, the Chaos organization, which did the high availability operating system, the precursor to the TOS operating system that we use today. The LLNL organization is our primary one. So we have organizations like the Flux framework, where it's sitting with its own collection of plugins. But how to actually visualize that and put a lens on that so that you can actually find the connections between all these things has been something that we've actually been able to use GitHubcom and again, GitHub Pages and Jekyll to build a lens into that. So we have a front-end portal, software.llnl.gov. And the idea here is there's one site where you can go to look into what are all the different repositories, right? The GitHub.com search will get you part of the way there. You can do things like searching in code. You can do things like filtering down on repository name. But it doesn't, at the moment, give some of the clearer, narrowing down to things like, I want to look for code that has this particular language, that's maybe in this particular domain. Maybe it's HPC, maybe it's multiphysics, maybe it's math simulation, something else. And how to actually drill down to that. These are problems now that the federal source code work and code.gov are attempting to solve by having a central location where all the federal agencies can actually put their code repositories, their code inventories, and make them available. This is some work that we did, again, kind of in parallel or just before, to actually put a lens onto our own repositories and our own source code internally and make that visible externally. So I won't belabor this too much, as we talked about it quite a bit in the keynote, but the federal source code policy is one of these great new things. There is a lot of change happening in the government around open source, consuming open source, developing and producing open source, as well as talks about inner sourcing. So yesterday there was a training session that talked and dealt with how to inner source. So essentially internal open source development, where you have projects internally that you open up to the rest of your employees to work on, to collaborate on, to suggest ideas on, to fork, to pull requests, to get all these things together. And I think the federal policy here gives a lot of avenues to start laying the groundwork for government to, in a lot of ways, catch up. We are a bit behind in terms of what the open source community is doing. And what this allows us to do is all get oriented in the same direction, to start to take advantage of some of these resources like GitHub.com, the integrations that it affords, and the work being done at other agencies. Since we're a national laboratory, again, growing out of the Manhattan Project age, where no one talked to anyone about what they were doing, no one knew anything, that's really a lot of what the culture still is today in government. You have groups inside of various different agencies, our own and other agencies, that don't necessarily talk to each other, that don't have a way to see into what each other are doing. And as Alvan mentioned, this leads to a lot of duplication, right? That $6 billion a year in software procurements is one of the side effects of that. And by orienting ourselves in a direction where agencies can actually see that another agency, maybe DOE can see that the FTC is doing some work to get trade information, or some of the National Forest Service data for visualizing geophysics and climate analysis, that we can actually start to share these projects. And rather than each of us developing our own project with, let's say, 5 people, now we can put 10 people pointed in the same direction. And I think that's a great opportunity going forward. I think we're going to have some great developments, and I think there'll be a lot of new upcoming work coming out of that as the pilot rolls out, as the code.gov site rolls out in the next few months, and as agencies start to get aligned with each other and start to get some visibility into what each other are doing. So currently, this is a small slide. I had to cut it down. The original list was about 1,800 government agencies across the world that have organizations on GitHub. So here it's a lot of US organizations, but there's a lot of work being done in other countries. UK has a lot of work. There's a talk, I believe it's a keynote tomorrow, on what the UK is doing with open source and open government, open data. These are the terms that, again, very prominent in the open source community. They're not new for most of them, but in the federal world, in the government world, a lot of this is sort of new to many folks involved. And so we're working out that, but the idea is that we're working that out together and getting pointed in the same direction. Some of the early work, again, 18F, the White House, NASA, NOAA, various different DOE national labs are all pointed in the same direction. See a couple people taking pictures real quick. So we could probably make a really nice slide. We should talk to some of the government GitHub folks that are actually have this to make some sort of nice deep visualization. And what I want to say is there's actually a government community that's grown up inside of GitHub. So one of the things that Chris mentioned was these forums. And while there's not a forum necessarily for government at the moment in the way that he showed, there is actually a community growing up inside of GitHub where government employees are able to meet, share best practices, to share information like, hey, has anyone worked on the security policy, getting the security approval for running a particular piece of software? You know, every agency repeating this process over and over and over again is saving no one anything, really. So again, there's a lot of work being done. There's a lot of work that's going to be done. I think that the next coming months are going to be very interesting. The LLNL open source Twitter account is actually sending out notices, a newer one where we're sending out information about the work that we're doing, about new projects that we have. And we very much welcome those that are interested in getting involved. If you have a project that you think could solve some sort of problem, if you have some sort of expertise in file systems or compilers or just how to make someone's life easier. A lot of times in these HPC systems, we have a lot of over-complexity. Sometimes that's good. There's a lot of complexity in the system. But a lot of times, there's a much simpler approach that the rest of the community has found that we could take advantage of. So at this point, I want to say thank you and open it up for questions. There is a microphone. If you can come up and ask your questions to the mic. And we have about, I don't know, 6 minutes.
I wonder if you could talk briefly about any challenges that you have encountered trying to move DOE and LLNL to open source.
So it's a good question. So what are the challenges around moving DOE and agencies, national laboratories like this into open source? One of the biggest challenges actually revolves around the type of work that we do. Because our portfolio is so diverse, it covers everything from this is pure computer science, there's no sensitivity, it's all very foundational, a lot of the stuff that I showed here, all the way up to things that are classified and export controlled and have all sorts of other limited release restrictions on them. And the reality is that a lot of times these things can become fuzzy for developers, right? Especially if you're working in both areas, detangling those two things. And the reality is that we have a lot of guidance for what it means, how you have to actually get something released. But there's, at the end of the day, it's generally a lot of bureaucracy. And I think a lot of the work that we're doing right now as we head into this next year is going to be breaking down those barriers and trying to ease the processes and try and separate out things that are clearly can be open sourced and developed in the open and things that do need that extra level of scrutiny. Because the end of the day is, when things goof up on the classified and export controlled side of things, people go to jail. So it's actually something that employees have to care about. Yeah.
Thanks for talking.
Sure.
Out of curiosity, I was wondering what the state of is of interagency APIs and public APIs, and where do you see that going in like 5 years?
The state of public APIs. So I think a lot of this is agencies actually moving to embrace APIs that are in the public already, right? Rather than reinventing our own wheels. Some of the work that Alvan sort of alluded to through the issues on the code.gov website issue tracker on GitHub are things around APIs. So one of the big piece there is that's not necessarily going to be the source code for all the government or where the source code's hosted. A lot of times it's still going to be hosted internally at the various agencies. But creating these sort of open APIs to get the data into and out of code.gov is going to be one of the questions that, well, it is one of the questions that's being discussed very actively on the issue tracker. So I think those sorts of APIs continuing to work together and also embracing open standards, right? Rather than developing our own cryptography or transfer protocols or all these sorts of things, there's a lot of industry backing behind doing these things already. And the reality is, and history has proven out, that the proprietary solutions generally don't work as well. They don't see the adoption, they don't see the same level of performance, and they don't see the same level of security, broadly speaking. Cryptography is a big example. So I think adopting things that are happening in the open source and not reinventing our own wheels will be one of the main uses of APIs.
Hi, Byong from SourceGraph here. Thanks for the great talk, and I'm actually live blogging it, so thanks for sending me your slides as well. I was wondering if you had any stories of other government agencies, some of the logos on that slide, kind of reaching out and using some of the libraries that you presented in this talk, and how has that interaction been? How do your developers work with their developers? Do they file issues? What's that conversation like?
Yeah, so if I just hit on some of the ones that I showed as some of the examples, we have things like Slurm, these job schedulers that are used across multiple different data centers. And one of the benefits of being out on GitHub that not every agency employee has to get accounts on every other agency in order to actually work on the code. And it also cuts down on the alternative, which is essentially tar something up and send it in an email, right? Not a very efficient process. It turns out things like GitHub have solved that problem largely. So that sort of sharing and actually doing things in the open on GitHub eliminates those barriers. We also have some things that are more sensitive that we collaborate on, where collaborators do have to get accounts on each other's systems. And that's often one of the biggest slowdowns to collaborations. Since we're a federal agency, we live on the fiscal year. We're at the end of FY16. October 1 starts fiscal year 17. And projects oftentimes only run for 1 year. So if any delays in actually starting that collaboration can really hurt the developer, or what the developer can actually get done. In terms of actually working and collaborating on different things, I think there's a lot of other examples. Some of the ones I showed here on the slide, like actually the NSA has a fairly popular project right now for sort of operating system configuration hardening. I think it's very interesting, right? It's a problem that we all face, and we all learn little pieces of the puzzle, and we should put those all together.
Ian, I'm Jamie Jones from GitHub's government team. I just wanted to give a quick note for people in the audience and watching at home. You mentioned government people getting involved on GitHub. Government.github.com is actually the best practices community you were mentioning before, which is open to anyone with a state, local, or international government account to come and collaborate and talk about what's going on. So that can answer some more of everyone's questions as well as help them to get involved. So easy plug.
Great. Thank you, Jamie. Yeah, and the slides will be up on speaker deck after the talk, and the link is there as well. So you can find all the links and references there.
Hi, thank you for the talk. I'm a UCLA student, so in universities, one of the growing fields is analyzing big data using supercomputers. Sure. And you mentioned Sequoia as that's a very strong computer, and I know a lot of companies like NVIDIA are creating efficient small supercomputer or server racks to use. Where do you see the future of that be in like a university? Because it's kind of hard to it's a lot of money. So just wanted to see your point on that.
Yeah, I'll answer real quick because we're running out of time, and we can continue offline. But I think that'll actually open the doors to a lot of these universities. But they're still going to have a lot of the same problems, right? Because you have GPUs, you have these very heterogeneous resources, you have larger file systems if you actually want to have the data. So we're going to run into the same problems. And I think what it's going to do is move a lot of the software that we've been developing that I talked about from this is a problem that only the federal government does because they're the only ones that have $1 billion to spend on a supercomputer, to now, like you said, universities and industry and smaller time operations being able to get the same sort of computing, but they're still going to run into a lot of the same I/O, scheduling, data storage issues that we face. All right, thank you very much.